Bah, c'est toi qui me dis. 10h10 ? Okay. Chut. Okay, good morning, everyone. So today, welcome to the third lecture of our QX01 lecture series on Introduction to Quantum Information and Associated Technologies. So let's have a look at the planning with the actual right dates, because I realized that for the last two times there was, well, pretty much all wrong dates, so now it should be the right ones. So we've done the first two lectures, and today we're going to do the third one, so it's an important one. It's about the quantum bit, the qubit. So we already discussed it a little bit last time, but we're going to really go into the topic today. And then next week, it will be about multiple qubits and the notion of entanglement. I mentioned that before, very important in quantum technologies. And then we'll carry on with measurements, operators, and so on and so forth. So the program for today, so there'll be 5 parts. Hopefully, we'll be able to finish them all today. If not, then it's okay. We'll finish next time. So first, I already started that last time, so the comparison between bits and quantum bits, of course. Then there will be some mathematical representation of a qubit. We are going to do some math today. Then I will talk about a very nice geometrical representation that is used a lot in quantum technologies for qubits, and it's the notion of a Bloch sphere and how we can represent a qubit in a basically 3D representation of a sphere. Then I will talk about an example of a simple qubit, and for that I will take the photon, the single photon as a qubit, and in particular I already mentioned that I will talk about how we can encode a quantum bit onto the polarization state of a photon. And I will give you some demonstration of what we actually do in the lab every day. And then I will finish by some more math, where I will talk about the dual space of a ket. Remember that? I mentioned that there is the ket part of a quantum bit, but there is also a bra to make a bra-ket. So all of this seems to be yet still a bit unclear, but hopefully it will get clearer and clearer. And today I will introduce the dual equivalent of a ket, which we call a bra, in the dual qubit representation. Right. So first of all, so I already showed that last time. So qubit stands for quantum bits. So we saw before, and we know that the classical bit has 2 outcomes, so it's either 1 or 0. But a qubit, it's something more than that. It's something that has also 2 states, so 0 and 1. Except that in this case, these 2 states can be in a superposition of the 2. So they are both 0 and 1 at the same time. Okay? So if I want to define a quantum bit, here we go. Here's the definition, the more general definition of a quantum bit, where psi is alpha times 0 for the 0 part of the qubit, plus beta times 1, where 1 is the 1 part of the qubit. So these coefficients, alpha and beta, are actually complex numbers. We will see that this is very, very important. This is an extremely important property. And this also has some physical meaning to it. We also like to work with normalized vectors or normalized quantities. So in this case, we have this relation that alpha squared plus beta squared equals 1 with modulus of alpha. So let's write that down, actually. I'm missing a chalk. So the qubit, the more general qubit, psi, so we will see just in a moment that this can be seen as some form of a vector, is a coefficient alpha times the state 0 plus beta times the state 1. And so alpha and beta are complex numbers. And they verify. So again, we will see that later on. It's not a big deal. It doesn't have to be, but it just makes things simpler. That the overall vector phi is normalized to 1, and therefore that implies the condition that alpha squared plus beta squared equals 1, which is in complex notations that alpha alpha star, complex conjugate, plus beta beta star equals 1. So we have, for a qubit, we have two states. We have 0 and 1, like the classical bit, despite this weird notation that we like. But the novelty really now is that there is the fact that both of the states can be in a so-called superposition state and are both available at the same time. And that's one of the key elements for quantum technologies and the power behind the applications of quantum technologies. So this notation, we already talked about it. So this is the so-called bra-ket notation, or also the Dirac notation, because this gentleman, Paul Dirac, who introduced that, so physicist. And we will see later on how this relates to the physics. So today will be mostly used as a mathematical notation, but there is some physics behind it, and we will see that at a later stage. So how do we actually picture that? Because superposition of states sounds like some weird physical effects. Well, it's okay. You can decide to do some math and say, well, I can say that this qubit, the way I introduce it, could be a vector. It's a vector. So we know vectors, and I can write it alpha 0 plus beta 1, where 0 and 1 are two vectors themselves, and those vectors, in the standard way of a 2D representation in space, could be the two unit vectors of the 2D representation of this vector, psi. Okay. So we have a 2D vector now for a qubit, rather than just a 1D number, which is 0, 1. We have a vector, so there is various representation. We will have to use these various representations. So this is one of them, and this is a standard representation of a vector. So you have two coefficients, alpha and beta, and you write it in a vector column. You can also say that I can write this as being alpha 1, 0 plus beta 0, 1, where the vector Ex is along the x-axis and it's of coordinate 1, 0, as in Ey is along the y-axis, is the coordinate 0, 1. We can also, and we will see that very soon, we can also manipulate. So here is the most general vector. It's a 2D vector, so psi. So again, this is things that we know from classes from before. So we have our xy plane with the origin. We have the two unit vector, Ex and Ey. And the most general representation of a vector, so this psi, can be, anything written as in alpha Ex plus beta Ey. I can also define another representation, and this is usually what we do in math and physics, which we call the polar coordinates. So we will see why this is interesting. So polar coordinates, where you define now the position of this point here, so where does the vector points, not by x and y coordinates anymore, but by two other coordinates, which we call rho and theta, where rho is the, let's take another color, where rho is the length of the vector, and theta is the angle of the vector compared to the x-axis. So again, this is standard. We did that when we were smaller. So we can define the coordinate rho and theta. And the difference here is that we can, so we said that these alpha and beta are complex numbers. So we can define a complex number, z, which would be rho cos theta plus I rho sine theta. And that would be the complex representation of this point here in 2D space. We can write it like this. So alpha plus I beta is x plus Iy in standard. So this would be the x representation, the x projector of the vector on the Ex, and the y projection of the vector on the Ey axis. And this can be written also in that manner, which is rho exponential I theta, which is the same writing as here. So why we use that? Because, well, as we will see, we can decide to take a qubit in one position and put it in another position. Okay. So if you do that, again, if you say, okay, I manipulate my qubits, so I go in one state of a qubit to another state of a qubit. So I will show you today how we actually do that in the lab. And we can do that, meaning that what does it mean is we can make a rotation of this vector. So we can introduce a rotation matrix, so R theta, which the most general way is cos theta sine theta minus sine theta cos theta. Okay. And we can decide to take that vector, apply rotation, and get another vector pointing in another direction. So say, does this direction. And now we call this one psi prime, and we can write it psi prime. What we have here is that psi prime is simply the rotation matrix, which is a 2D rotation matrix times psi. Okay, rotation matrix. So it's a 2D dimension because, well, we are in the XY plane. And we will see later on that we do that all the time on qubits. We manipulate qubits that way. And though this rotation is actually what we will call later on a gate. Right? It's a quantum gate where you manipulate the state of your qubit from one state to another by modifying the coefficients, for instance. Okay? You could decide to go from this state, which is 0, which is not a superposition state, to this one. Okay, and if we want to normalize, we have a normalization factor. We will see that later on, but we can do that, we can manipulate, and what the equivalent would be simply that we are on the y-axis, and we rotate by a certain rotation theta to be in a superposition state or in a new vector state, which is with the same amplitude along the x-axis and the y-axis. We just did a rotation. So rotations on vectors are actually gates on qubits, as we will see later on. In fact, what we can use for qubits to manipulate them is what the so-called Pauli matrices. So here you have the 4 Pauli matrices, or the 3 plus 1. So sigma 1, sigma 2, and sigma 3. Sigma 1, sigma 2, and sigma 3, and the identity matrix in 2D, which is 1, 0, 0, 1. And you can show, first of all, you can show that these 4 matrices are what we call emission matrices, which are, a family of matrices that have special behavior. We will just talk about in a minute. The first thing you can see is that there are complex numbers in these matrices. Another, I'm not going to demonstrate that today, but another important feature is that using these 4 matrices, I can generate any matrix, any Hermitian matrix, any 2D matrix, as a linear combination of these 3 plus 1. Okay. And associated to that, there are some properties of commutation and multiplication between them. So for now, this looks a bit not necessarily clear, but we'll get back to that later on, just to know that these matrices, as you can see, sigma I, sigma j, and sigma k, and so 1, 2, and 3, where a, j, and k are 1, 2, and 3, they are linked with each other, and you can go from one to the other. Okay? And again, so you can manipulate those, and you always end up being in this sort of space of 4 matrices, or Pauli matrices. And you'll say, okay, so what's the deal with that? Well, we will see that, first of all, as you can generate any matrix with these 4, that means basically that for future computation that we will show, we can use them as basic gates, okay? So those gates, if you remember in the second lecture, I mentioned that you have some classical gates, like AND and NOT and so on, where you can, using them, you can generate all the others by a linear combination of them. Well, it's the same thing here. And that's why those are particularly important. Okay? We'll get back to them later. And we will see what they do, what they are on specific qubits. But the take-home message here is that they will play a crucial role as quantum gates for our computation, quantum computation to come. So I use a term here, I used it before, is the fact that these matrices are particular matrices. So I don't know about you, but it's certainly not, when you learn to manipulate matrices, you don't usually learn to manipulate Hermitian matrices, okay? And so those matrices are particular because they're Hermitian, and it's just not because of the name, but it's because they have this particular property where an Hermitian matrix, A, is equal to itself with this symbol here, which we call dagger, okay? So let me explain, and let me show you what it does. So again, you will see later on that in quantum technologies, you know, it's a bit like a board game. You know, there are some rules. You just need to get on with it and apply the rules. So here, the dagger rule is a rule like another one that we need to apply for our quantum gates and for our application in quantum communication and quantum computing. So another thing is, as you can see, I'm going to start to use the notation hat here. So this is the so-called hat notation. Okay, so this is the hat notation, like a, you know, hat, which will be expanded later on. For now, whatever, we have it. I don't have to put it. I could not put it. Doesn't matter. Okay, I could use a hat, but I could use, I don't know, the chair notation or anything. Doesn't matter. Okay. We will see later on that there is for a physical meaning, we like to put the hat because behind that there is a measurement, a physical measurement. But for now, let's not worry about this. So A is an Hermitian matrix if A, with the hat, doesn't have to be, but equals to itself, but with this dagger sign. And what is this dagger sign? This dagger sign, as you can see here, is the combination of two things. It's the combination of the complex conjugate and the transpose property. So if you have this, so dagger is complex conjugate, so complex conjugate operation, conjugate, plus a transpose operation. So let's take an example. Let's take sigma 2. So sigma 2 is 0, I, minus I, and 0. So if this is a Hermitian matrix, that means this should be equal to sigma 2 dagger. Well, let's see. So sigma 2 star, complex conjugate, is 0 minus I, 0. Right? And now I take the transpose. So the transpose is basically take the symmetric of the matrix as compared to the diagonal line of the matrix. Okay, so you just mirror flip the matrix. This is what the transpose is, with all coefficients. So here is rather simple because you only have 2D. And it gets a bit trickier with 3D and more, but it's the same idea. You just flip all the coefficients. So if you flip the coefficients, then those don't move, and I just flip these two. And I find I minus I. And this is called the dagger operation. Sometimes also called cross, but personally I like dagger, and I'll let you figure out why. And this is indeed equal to sigma 2. We started with. Okay? So sigma 2 is emission. Okay? So this is very important. Okay? Those have to be, so whatever matrices we're going to manipulate, so those are gates, and whatever gates we're going to manipulate, they have to have this property. Not just because it's a mathematical artifact or consequence or whatever, but there is actually a physical meaning to that we will see later on. I remember I told you, and this is why we put this little hat. It's not just because it's a mathematical object, but it's because there's physics behind it. Okay? And the physics behind it is a measurement. In physics, we cannot measure a superposition. We can only measure the result of a superposition. But we will see that again in some examples. And as we do a measurement, then these matrices, which we will call operators, have to have this property in order to be of physical meaning, something that actually makes sense and can be measured in a lab. Right. So here we go. Polymatrices are quantum gates. So in fact, you will see that other names of sigma 1, sigma 2, and sigma 3 are called X, Y, and Z. So those are the three Pauli matrices, plus the identity matrix. And the equivalent, so for instance, we saw the NOT gate in a classical computation, where you just flip the bit 0 becomes 1, the bit 1 becomes 0. Well, the equivalent in quantum gates, again, we will see that later on, but that's a sneak peek, you know. It's the X matrix, okay, where we flip. You can do it, you can already do it. We could do it on the board, but I don't want to spoil it now, where by just applying the X gate, which I believe is the sigma 1 Pauli matrix, we will flip the qubit. So what was 0 becomes 1, what was 1 becomes 0. So it's the strict equivalent to that. And so in fact, what we have here is our first circuit. So it's our first quantum circuit, where we have an incoming qubit, we have a Pauli matrix, the X matrix, which is equivalent to a NOT gate, and we flip the qubit, and we have another state, psi prime, which is applying X on phi, and this is our first quantum circuit. It's the easiest you can do. You have a qubit, you make a gate. I will show you an example of how we do that with photons, and then you end up with another bit, another qubit. Of course, the easiest representation in terms of circuit for the identity matrix is just a line. Right? So we usually do not use this matrix because, well, by default, everything is identity. If you don't do anything, then this is an identity matrix. Okay? Or an identity gate. Good. So, like I said, it's going back to qubits and the notion of probability. So that's another important aspect that, again, hopefully will get clearer as we walk through the different lectures. But we said a qubit is in both 1 and 0 at the same time. But what we also said is that, as you can see here, is that this qubit, so now we know these coefficients are sort of the equivalent of the vector coefficients. They are normalized, so there is normalization factor here, we talked about already. And what we can see is that these parts, so alpha and beta, is like a bit of a dial. You know, you can dial and change the weight of alpha and beta at will. So for instance, you can go from the state 0, because if beta equals 0, so you tune your dial all the way down to alpha, and beta equals 0, then you have the 0 state. Then if you dial the other way, so you dial up to beta, then alpha equals 0, and you end up with the 1 state. So of course, those are not very interesting because, well, these are classical qubits, 0 or 1. What is more interesting is, you understood that by now, is the fact that we can have both at the same time. So for instance, if I decide to put the dial somewhere in between, I've got an exact superposition of 0 and 1. Superposition in the sense that now there is an equal weight on 0 and 1. Both are equally probable. Both are equally plausible. Okay? And that's much more interesting because this uses the superposition effect of quantum mechanics, and then there's a bit of a problem here, but never mind. The superposition effect of our of quantum physics in order to use the qubits as with their full range. What's going on here? Not quite sure. No, doesn't matter. Doesn't matter. What was here, basically, I don't know why it's not here, but what was here is what you saw before, is, if you remember, the Schrodinger's cat, which was, both at the same time dead and alive. That's what I represented here. It's in this case, in the Schrodinger's cat experiment, is in a 50% chance superposition state of being both and dead at the same time. Okay? Alive and dead at the same time. So superposition is, of course, much more interesting. And what we do here, and we talk about probability, and I will show you, how we do that and how it makes sense, because those coefficients, when we manipulate a single qubit, so a single photon, becomes, or are equivalent, well, in fact, they're not equivalent, they are probabilities of finding a 0 or 1. Because that's the only thing you can say, right? This is in a superposition state. So you don't know what you have in advance. You don't know if you will have or you have 0 or 1 because it's both at the same time. What you can tell, though, is that as you move your dial, you can change your dial so that one is perhaps more probable than the other one. Or in this case, both are equiprobable, which is, again, as we will see, the most interesting case where there is an equal probability of having 0 and 1. Right. So the Bloch sphere representation. So unfortunately, I usually have a football to represent coordinates, spherical coordinates. I don't have it here, but it doesn't matter. We'll figure it out differently. So let's have some going back to classical mechanics, classical physics. So you know that in classical mechanics, you can represent, I mentioned earlier, a 2D representation in a XY representation, so it's a Cartesian representation. We can have the polar representation, where you say, okay, I've got the length of the vector and the rotation theta. That's in 2D. And in 3D, there is another representation for coordinates that we use. It's called the spherical coordinates. And this is it. So you have to imagine a sphere. And the question is, how do I represent a point in 3D that will basically lie on a sphere? Well, you need three numbers. You need r, you need theta, and you need phi. So what are these r, theta, and phi? So r is basically the diameter, so it's the length of the distance to the center. So if m is our point, then r is the distance OM. Okay? And it's basically the radius of our sphere. So that provides us if I start from here, I go at the r distance, and I don't go further or closer. Okay? So I'm here. Now the question is, where do I go on this sphere? I can go anywhere on this sphere. So that's why I need two more coordinates. And the two more coordinates, the first one is theta. So if I have x, y, and z, and at the center of the sphere, then theta is basically the angle that makes the OM vector, so O is the center and M is the point that we want to look for, the coordinates, so here OM. Then theta is the angle with the z-axis, okay? So that's good. So now we have r, we have theta, so we are in a plane like this, which is a sphere, and we need to know, sorry, we are in a sphere like this, or in a circle like this, sorry. Now we need to know where we are on this circle. So for that we need the third coordinate, which is the phi coordinate, which is the angle between the x-axis, so this axis here, we see here, and the projection of OM onto the xy plane, okay? So basically what you have here, spherical coordinates, is what we use for longitude and latitude. So theta and phi are actually longitude and latitude. Actually, theta is the co-latitude, but it doesn't matter. So if I want to represent a point in 3D, so this is the center, I'm the center. So first of all, I look at the radius, distance r. Then from the start, from the z-axis, I move by theta. And then I turn by phi in the xy plane, which is the equatorial plane. If I take the Earth, that would be the equatorial plane. The z-axis would be the North Pole. Then I just turn phi, and I find the third point. So now I've got r, I've got theta, and phi. And by doing so, I can represent any point in 3D space that would lie on a sphere of diameter r, and with coordinates, latitude and longitude, theta and phi. So this is classical mechanics, no problem with that. We can find, so the OM vector, the vector from the center to this point that I want to represent 3D, would have three coordinates in Cartesian coordinates, x, y, z, which will look like these three, so r theta cos phi, r theta cos sin phi and r cos theta. Okay. All right, so that's classical mechanics. And now, what is nice is that we can use this representation of a point in space to represent our qubit and to represent every single state of a qubit in the 2D space of the qubit 0, 1, but with a 3D representation. Okay? Now, the difference is that this sphere here, the diameter of this sphere, sorry, the radius of this sphere is 1, right? Because we said the vector, the psi vector, I erased it, the qubit is normalized to 1. So in terms of vector, is a normalized vector of norm 1. Okay, so this sphere has a radius of 1. And now I can represent my qubit, psi, in this sphere anywhere by simply these two coordinates, theta and phi. And you can show that any of these, so any state of a qubit can be represented on this sphere. That's what we call the Bloch sphere, where in this case the north pole is the 0 qubit, the 0 state of the qubit. 1 is in the south pole, so it's the 1 state of the qubit is in the south pole. And then you've got the x and y, and x and y would be, so in this case for x, so long x, you would have, in fact, the state 0 plus 1, normalized to 1 square root of 2, or 0 minus 1. It depends if you're on one side or the other side. And for y, along the y-axis, what you get is the 0 plus I1 qubit and 0 minus I1 qubit if you go on the other side. So you can see, so it's a nice representation. So we like to use the Bloch sphere to represent a qubit in 3D geometry. And we can rewrite, so we can, let's write that. We can rewrite our qubit in this representation of the Bloch sphere by using theta and phi. And the good thing about that is that the complexness, the complex behavior of the coefficients appears here. Okay? So now I can rewrite my qubit, the more general representation of my qubit, as in this, so cos theta divided by 2, 0, plus sine theta divided by 2, I exponential I phi 1. So I'm not going to demonstrate how we get those. This will be done during the tutorial works, but it's not very complicated to go from this representation to this representation. And as I said, so this is a very useful representation because here we can clearly see that there is a complex part with this exponential. So that's good. Because here, all we know is alpha and beta are complex numbers, but we may forget that, or we don't know, maybe one is real, both, we don't know. Here, there is no problem. This is a real part, this is real, but this is complex. Okay? So it's quite useful. And we can, I think I have, and we can represent, so each of these qubit states, or any of these 4 states, by simply changing the values of theta and phi. This will give us any representation of phi. So a quick note. So sometimes this sort of so this representation is what's called an automorphism in mathematics, and sometimes it's also called, so it's used for probably some very good reasons that I don't know about, and sometimes it's called the well, for mathematicians it's called the Riemann sphere. And it's an automorphism because you basically go from a 3D representation to something that looks like a 2D, well, not that looks like, it is a 2D space. Okay. But there is a similarity between the two. And that's why we like to use that, because now it gives us a geometric view of a qubit. So now, if I want to look at a particular state vector, then I just need to look at the Bloch sphere coordinates. So for instance, if I use the qubit Q in a state, so 1 square root of 2, 1i, which is something like this. Oops. Let's, too much coffee, clearly. So now, how do I get this state using this representation? Well, it's very easy. For r, theta, and phi, in the classical representation, then I've got 1. We said r equals 1, so no matter what we do, because it's normalized, theta would be pi over 2, and phi would be pi over 2. Okay, so let's check that. I'm going to replace now theta and phi into here and see if we end up with this. So if I replace, I've got cosine of pi over 4, 0, plus sine of pi over 4, exponential I pi over 2, 1. This is 1 over square root of 2. So let's take another color. This is also the case. And this is cosine pi over 2 plus I sine pi over 2. Right? And this is 0, and this is 1. So here we go. What we have is indeed equals to 1 square root of 2, 0, plus 1 square root of 2 times I, 1. And this is same state. So this coordinates for theta and phi give us this state. And I can generate any states of a qubit by changing theta and phi. And again, you'd say, okay, why do we need that? Well, first of all, because it gives us a geometrical representation of a qubit, and we can see how we can, so the pointing of the qubit gives us the direction, and sometimes it's very useful to do that. We will see later on when we manipulate the qubit with several gates. You know, you do so basically when you use gates, that means the qubit will point in different directions. So once you're like this, and then you use a gate, you might be like this, and another gate like this, and then like this, and so on and so forth. So it's a nice way of picturing the various manipulations on the qubit. Plus, as I said, the good thing about this representation is we clearly identify the fact that we have complex notations and complex numbers by this part. Right. Okay, so this was for some math. Now let's do some physics. So during this series of lectures, I will use mostly two physical systems because they are kind of the easiest, or at least to me. The first one we're going to do right now is to represent a qubit as a photon, or at least the polarization state of a photon, or the spatial mode of a photon. We will see what that means. So that's the first representation. And the second representation is what we call the spin of a particle. And we will take a simplest particle you can think of, which is an electron. So we will use both of those physical systems, which people use in the lab and trying to make quantum computers with, as our physical representation of what we see during these lectures. There are many other systems, like atoms and ions, superconducting qubits, circuits, and so on and so forth. We cannot cover everything. The last 1 or 2 lectures of this series will cover those aspects. But during our main lectures, we will use the photon and the spin of an electron as a physical representation to help us to make physical sense out of all of this. Right, so for today, the photon. So we will see how we can use the photon of light as a qubit. First of all, I need to do some quick reminder. Hopefully it's a quick reminder. If it's not, it's okay. It doesn't really matter because I'm not going to go into the physics of that. But let's go back to some basics. So if you know that already, then this is good. It's just a reminder. If you don't know that already, then you will. So light is an electromagnetic wave. And we know that since Maxwell, that electromagnetic waves, or light, can be basically described by these 4 equations. And in these 4 equations, we have various terms, so we're not going to go through all of them. But what we have is we have the electric part of the electromagnetic wave, which is the electric field E, and the magnetic field B. And if you manipulate these equations, if you just take that, you shake, and then at the end, what comes out by some calculation is what we call a propagation equation, also called D'Alembert equation, which looks like this one, okay, where we have this operator delta. I will have a quick reminder of what that is, applied to E, and 1 over c squared, where c is the speed of light, times a time dependence, so second derivative in time of the electric field. Okay? So let's go back to basics. Again, if you're not up to date on electromagnetic theory, it's okay. We don't actually need that. We just need some basics. So the electric field is actually all we need to represent an electromagnetic wave. And I'll show you why in a minute. So electric field is all we need. So all we need is an electric field. And if you solve Maxwell's equations, which are the achievement of hundreds of years of, or decades at least, of physics of electricity and magnetism, then you end up with many equations, and Maxwell's equations can give you many, many equations, but there's one in particular, that is a propagation equation, for the electric field, which is given by delta E. So E field, so it's not represented here, but so all this quantity E, B, J, and so on, they're all vectors. Huh? It's the bold notation, but they're all vectors. So delta E equals 1 over c squared, second derivative in time of E, where c is the speed of light. Okay. In fact, and c is a combination of these coefficients. I mean, it's equal to 1 over these two coefficients. But whatever, doesn't matter for now. So I've got this propagation equation. So what it means is that we have an electromagnetic wave that can propagate in time and space, and the propagation of this wave is governed by this equation. With, I didn't mention, but with some hypothesis, like we are in vacuum, there is no charging effect around or current or whatever, but it doesn't matter, it's just some light. So if I use a laser pointer, I can apply this to that. Okay. This operator, I said I would say something, just to. So this operator in Cartesian representation is simply the second derivative in space of whatever I apply to. So for instance, let's take a very simple case. So in 1D, so assuming I have an electromagnetic wave propagating along the x direction, then in 1D along x, then I can drop the vectors. I can say that this is along x, so I can drop the vectors. Then this equation would look like something like this. All right. So if I do that, then I can find a solution, and the solution to that are what we call plane waves. Plane waves are solutions. And what does it look like? Well, you've got an example here, a nice little video, where this is the propagation of an electromagnetic wave along the x-axis, which verifies this equation, which is a plane wave. So plane wave, I'll come back to that later, but meaning that it's just an oscillating function as a function of time and distance. So in blue, you have the E field. You can see the electric field oscillating. And you can see in red the magnetic field oscillating as well in complementarity to the electric field. That is because if I take those equations and shake them differently, then I would end up with the same propagation equation here, but for B field. But it would look the same, would be the same. So that's what I was saying earlier, is that the good thing is we don't have to worry about knowing B so much, because once we have E, then thanks to Maxwell's equation, you can see here, for instance, once I've got E, then I can derive B, no problem. So that's why usually when we talk about light, we say that light is the electric field component of the wave, and that's enough to represent light. So here's the propagation. So you've got the light propagating along X. You've got the electric field oscillating along the y-axis, and you've got the B field oscillating along the z-axis, and all of those in complementarity. We define what we call a wave vector. When you have a plane wave, you define a wave vector k, which has two purposes. This wave vector, it defines the propagation axis of the wave, so along x here. And you can see if k, so k would be something like k times u, where u is a unit vector along the x-axis. And k, this wave vector number, it's 2 pi over lambda. And lambda is what? Is the wavelength of this plane wave. It's basically the wavelength between the two maximum of this wave. Okay? And I just want to write that we have the wave vector k. K is defined by k times unit vector u, which is along the propagation axis with x, along x in this case. And k is 2 pi over lambda, where lambda is the wavelength of the wave. I never know. So for light, the wavelength is basically the color. So red is a certain wavelength, blue is a certain wavelength, microwave is a certain wavelength, gamma ray is another wavelength. Okay? The only difference is that the length of this wavelength is different, and that some of them we can see with our own eyes, some we can't. Some of them are harmful, some are not. So that's the first thing. Just a quick note as well is we usually define the direct coordinate, or the direct representation, I should say. There's a French word for it, but I'm pretty sure it's not directly. The direct translation in English is not the case. It's not the same. Doesn't matter. Which is u. So u is the along the propagation axis, along x. So in this case, E is along y, and B has to be the third finger in that order. So it's U, E, and B. And this has to be, you can rotate that as you want in 3D space, but those three have to be in this same order. So usually we have to represent U, E, and B in that representation in that order. That's what we call a direct representation of coordinates. And that only works with the right hand. It doesn't work with the left hand. You would need to have your finger like this. So that's that. Right? So how do we get to the photon as a qubit? Well, the next observation of light is that light is polarized. So light is polarized. And what is this polarization? So here you have some examples of light polarization. So here's the same background, but taking with polarizers. You know, you have that with some of the cameras, some of the phones now probably. And here you look at the bending of plastic ruler, and you can see the various colors. due to the fact that there are various, as the light goes to the ruler, the polarization changes as a function of the stress applied to the plastic. And the good thing is that light, so the polarization of light is actually given by the direction of the E field. Okay? So in this case, it's the same, again, it's the same nice drawing. You can see that the electric field is along Y. So if the propagation is this way, that means the E field oscillates like this. That means the polarization is like this. So the polarization state of the light is like this. And in this case is vertical. But I could also have the electric field like this. So if I go towards you, so the light goes towards you. If I'm like this, that would be one state of polarization, that would be vertical state. But I could also oscillate like this, then B would be accordingly rotated as well. Then E would be like this, and that would be the horizontal state of the polarization state of light. I can also be at 45 degrees, or minus 45 degrees, or any angle. So I guess maybe you see me coming, because, well, this, I could say, this is a state of light that I can call the 0 state of my qubit, and this could be the 1 state of my qubit. So vertical, horizontal. 45 plus the superposition of the two. We'll see that afterwards. So polarization state, this is one way of coding qubits on photons. It's probably the most, the easiest to picture, not necessarily the easiest to manipulate in the lab, but it's easiest to picture. And just, yeah, and another quick note, so I said earlier, so these plane waves, so what do they look like? Well, here we go. So we have the electric field, and so this, you can do it, and it takes no time, in 2 seconds. You take this, you stick it in here, and you will find that this solution for the electric field does solve this equation. And that's why those plane waves are a solution of the propagation equation for light. Okay? So I will write that because we're going to need that. So the plane waves for light propagating according to Maxwell's equation look like this. If we have plane wave solution, it's E vector equals E0, the amplitude of the vector, cosine omega t minus k, the wave vector, x, if I'm propagating along x. And E0 is where the polarization state points. So E0 could be towards y, that's what's represented on this graph here. So we have E0 along y. So that could be a 0 state vector. It could be a 0 state. Or it could be along the y-axis, so the x-axis, sorry. No, not the x-axis, because that's the propagation axis. Could be along the z-axis. And that could be the 1 state. Yeah, one piece of physics you need here is you could say, well, how about along the x-axis? Well, the electric field usually does not point towards the propagation axis. There are some very specific cases where it can, but let's take it that it cannot, so that the E field and the B field are always orthogonal, so always in a plane orthogonal to the propagation axis. Okay, this is something you need to know. So that means that the E field can be in any direction in this case, YZ plane, in a 2D plane, but not along the x-axis. And that's good, because that means that we can now use this polarization state, like I said, to be our qubit of 0, 1, or 0 plus 1, as we will see. Yeah, one, is that it? No, that's it for now. So, okay, so let's have a look. Oh yeah, no, I wanted to show you something before going to more math. So for instance here, so I've got this we will deal with that later on, these two. So I've got a lamp here, and here I've got two polarizers, and I'll show you how I can demonstrate that light is polarized by using these two polarizers. So those are two polarizers. So what do they mean? What does that mean, a polarizer? A polarizer is something like this, which doesn't look like much for now, but you'll see what it does. It's basically a material that lets only one polarization state going through. Okay, so in only one direction. So if I rotate it, I basically choose which polarization I want the light to go through. So here I've got a lamp, which is an LED, so it's got no particular polarization state. It's any random state. And so I put it on, and I put my first polarizer onto it. So that means that most of the light is going to be blocked, except the light that is going through the polarizer axis. So I don't know what the axis is. I don't know if it's like this or like this or like this. Doesn't matter, but I know there is one. So if I put it in, knowing that this has no polarization in particular, that means that I should have less light coming through, because all the rest is going to be blocked, and only the light that has the right polarization will go through this polarizer. So if I do that, I've got less light coming out. And now I've got a second polarizer, okay, and which is the same material, so it's got also one axis of polarization. And that means that if this axis of polarization is different than the one here, then it will block some of the light as well. If it's the same one, then it's like I don't have anything. And if I choose exactly to be orthogonal to this, so the two axes to be exactly orthogonal, that means that this guy cuts everything except his own axis, and this guy cuts everything except his own axis. So if these two axes are orthogonal axes, then nothing comes out. So let's see. So here I'm in a state where some of the light comes out, and now I turn the polarizer, and you can see the light is dimming and eventually disappear. I can carry on rotating, the light comes back to a maximum, which means that probably around here, the two axes of this polarizer are aligned. And then I rotate again and start to lose some of the light because the axes are not aligned anymore until they are completely orthogonal, in this case here, and all the light is gone. Nothing can go through. Nothing can go through because the first polarizer selected that polarization and the second one selected that one. And there is nothing in common in between. So there's no light coming out. So you can see here already how we can, manipulate or measure these polarization states and perhaps use them as qubits, and that's what we're going to do. So now, let's see how we can represent. So I give you a clue here, but let's carry on into that. So polarization state in optics, so this is known for 100 years. We know how to deal with polarization state of light, no problem. So polarization state of light, so it can be any state, but so it can be vertical, horizontal, 45, so diagonal, anything. But we like to have three states mostly, or three basic representation. So the first one we already saw is this one. So in this case is the linear representation. Yeah, you have to be careful here, because this is not the same as, my bad, this should be EZ and EY, because the EX is the propagation axis, so be careful, this should be EZ and EY. So we have the two, these are these two, basically. So this is EZ and this is EY, so I can have E like this. So this would be the linear basis, linear polarization, along vertical, horizontal. I can be at 45 degrees, so plus 45 degrees, or minus 45 degrees. I can propagate like this, or I can propagate like this. Then in this case, it's just a vector. So if it's a vector, that means this E field at 45 degrees will be EZ plus EY and EZ minus EY. But I can also have something very interesting in light also, is circular polarization. I can have circular right polarized state, or so right-handed or left-handed. So what it means is that if I write my electric field that way, so where I have the Z component plus the Y component, which are the same one, except that here I added a phase, a pi over 2 phase. You see? From this component as opposed to this component. Here there was no phase added. Here there is a phase added. And that makes a big difference, because this phase added will basically now make the polarization go circular. So the light propagates towards you, and the electric field points in a circular manner. So it does something like this. So this would be right-handed, or maybe left-handed, I never know, but what I do know, if this one is right-handed, then this one will be left-handed. Okay? So here we go. Those are polarization states. So I can use 0 and 1. That would be vertical and horizontal. But I can also use now the plus-minus 45 degrees, a diagonal, which is EZ plus EY, which is, well, 0 plus 1. So here we go. We have our superposition state. So this polarization state is the superposition state of being that way or that way. So here we go. In the linear polarization state along Z and Y, again, and this should be a Z here and here. Then we have, so this state is 0, and this state is 1. So we have our 0 and 1 in the vector representation. For plus minus 45 degrees, well, I've got EZ plus EY. So if I write, so let's write that down. So I've got E equals E0 cos omega t minus kx, and say EY, and I say that this is 0. For the other one, so this would be E0, this would be E1. I've got the same thing, except that now I oscillate in the Z. So we said, so X, Y is like this, and Z is like this. That could be 1. Our qubit state 1. And now for plus minus 45 degrees, or diagonal and anti-diagonal, then I've got E plus, which is going to be E0, cosine omega t minus kx, and I'm going to have Ez plus Ey. I can call this state plus, and now this state plus is in fact, is if Ez is 1, Ey is 0, then it's 0 plus 1. There we go, we have our superposition state here. Of course, there has to be some coefficients in front, normalized coefficient, whatever. This can be taken from that part. So it's 1 square root of 2. So this would be our 0 plus 1. Then the E minus would be cos omega t minus kx, Ey minus Ez, and that I can call it the minus state, and this would be, sorry, Ez, no, that's it, Ey minus Ez, and this would be 0 minus 1, and I would have square root over 2 here again as a normalization factor. All right, and now I can take the third one, the third basis, which is the circular polarization basis, where, remember, we said that the only difference is that now the second component has a phase here. It's got a phase of pi over 2. But a phase of pi over 2 for circular polarization we have a phase of pi over 2, which is an exponential I pi over 2 in complex notation. And that is I. So we've got here the state, which is 0 plus minus I. So 1 square root of 2 is 0, plus minus I, 1 square root of 2, 1. So we have another superposition state with this time a complex part. And remember, this is the state, this state, so sorry, this one, let's write it in blue. So this state, hola. Let's do that properly. Let's do it underneath. So this state is going to be 0 plus I1. That would be for one circular, so say circular right. And this is exactly the state that we had earlier, the Bloch sphere, you know, that we took as an example, right? So if I go back, oops, no, there, it's fine. No, this one, where we had pi over 2 and pi over 2. And yes, indeed, if I take that state, that's what we did. We took pi over 2 for theta and pi over 2 for phi, and we end up with this state. And the phasing here of pi over 2 is the exponential I phi that we had earlier. So in other words, that means that we can use polarization state of a photon as a qubit, because it's got all the properties that a qubit has. quick note, so often I believe the zero state, so you will see that if you start to look into books and internet and so on, so people use 0 and 1, but physicists like me, they like to use V and H to represent. So like I did here, I used plus minus, but so physicists like to use V. Let's put it in a bright color, so let's not forget that. And I believe that usually the 0 is the so-called vertical polarization state, and we call it V, and the 1 is the horizontal polarization state, like this. And as physicists, so what we mean by horizontal and vertical is usually compared to the lab that we are in, okay? So this, compared to this room, this is vertical and this is horizontal. So this would be plus, and this would be minus, and this would be circular right, and this would be circular left. Right. Okay, so that's that. Then it's very easy, because all we need now is a single photon. We want to say now to encode the polarization state of a single photon in order to have our qubit, because we know the polarization state can be used as a qubit. And luckily, light, like everything, in fact, quantum mechanics tells you that light is a wave, but it's also made of particles. And these particles are called photons. Okay? So it means that I can really manipulate single photons. It's far from trivial, trust me, I know what I'm talking about. But you can do that, and therefore use them as qubits. So if you're able to produce single photons, then here we go, you have your single qubits. So you may say, well, it's easy. You've got loads of photons in that room. And you're right. There is a tremendous amount of light, and therefore of single photons in that room. To give you an order of magnitude, a typical laser pointer, the power coming out of it is on the order of a milliwatt of power, of light power. A single photon is less than a femtowatt of power. A femto is 10 to the minus 15 watt. Okay? So in this room, which we have probably many milliwatts of light, that means we have a lot of photons, and we do. Except that those photons, we don't really, we don't control them. And as one major part of the physical implementation is to be able to control light at the single photon level in order to manipulate the photon as a qubit. But once you do that, once you can isolate a single photon, so maybe we will talk about this later, how we do that, then this is it. Then you're it. Because it's very easy to manipulate light, and as photons are particles of light, then it's very easy to manipulate photons, therefore it's very easy to manipulate them as qubits. And we've got here elements that we use in the lab to manipulate them. So this, for instance, is what we call a beam splitter. So it's a cube that will cut the light into two parts. So when the photon goes here, when the light goes here, half of the light is reflected and half of the light goes through. And this works for single photons. Single photon will behave the same way, except that a single photon will not be here and there at the same time. It will have to choose. It either is here or is there. But either here or there already is another way, which we'll talk about next time, of having a superposition state is to be in a spatial superposition of light. But the fact is you can manipulate them easily, so you can use what we call quarter wave plates and lambda and half wave plates, or lambda over 2 and lambda over 4 wave plates, which are basically some optical components that you can buy off the shelf and manipulate the polarization state of light. What do I mean by that? Well, I can, for instance, use a half-wave plate. So here, say I've got an incoming photon in the vertical state, and I use a half-wave plate, which is, well, basically something like this. And if I rotate that half-wave plate in a good way, then I can rotate, so I can go from this state to this one, or this one, in fact, any state. So I can rotate the polarization state of the photon. So I can manipulate my qubit. And in fact, I can make a superposition state. I can put it at 45 degrees. Or I can use it as a non-gate, right? Because if I do this, or not gate, sorry, if I do this, and if I rotate it along this axis, which I can with those optical elements, then I go from 0 to 1. And that's a not gate. That's the Pauli matrix X gate. So this is an X gate in optics. Very easy. I can use other elements like a quarter wave plate, which is another particular material, and I can go from a vertical state to a rotating state. I can use what we call a polarizing beam splitter. So I will show you a quick demonstration in a minute. And a polarization beam splitter, it's a cube like this one, but it's, in this case, it will not separate the light equally. It will separate the light by the polarization state, meaning that if the light comes in a certain polarization, it will be reflected. But if the light comes out with another polarization, it will go through. So a polarizing beam splitter, it's an object that would split the beam, the light beam, according to its polarization state. So again, you can see how useful that can be, because you can have a plus state with 0 plus 1, where you have vertical and horizontal, and now I can have an object that can separate these two states, which is called what we call a polarizing beam splitter. So we can, we can manipulate those objects very easily, like we manipulate polarization state of light in the lab. So once you manage to create these single photons, which is the hard part, clearly, but once you do that, then this is it. You have all these polarization optics to do so. So I don't know if you can see that, but I will do it anyway. So this is what we call a birefringent crystal. So this is a particular crystal, and that will have the property to split the light according to the polarization state. So all these components I just showed are basically more or less fabricated in this type of material. And this, so actually this is called the Iceland spath. It's a sort of ancient crystal that people use, and I believe Vikings used that as a navigation crystal. Because this crystal, as you will see, if I put it on a piece of paper with some lines, birefringence tells you that the different state of polarization will be separated. So if I do that, so I put it here, so I don't know if you can see, maybe I'll do it like this, perhaps. So if I'm like this, you can see only one line, but if I start to rotate it, you should see two lines coming out, right? To a maximum, which is somewhere like this. So this property, this birefringence property, So why do we see two lines? And clearly there's only one, it's not a magic trick. It's because the light that goes through, so the light from the room, has both polarization, and these two polarizations are separated by this crystal. So using these crystals, not just for navigation hundreds and hundreds of years ago, but we can actually, like I said, make them more in a controlled manner in these elements so that we can actually separate or recombine also different polarization states. Right. So I hope I convinced you that light seems to be appropriate for that. And let's see how we can go further. Quick word though, first, is that next time we will touch upon a very quantum mechanical behavior of particles, of everything in fact, is what we call the wave-particle duality. So in general, quantum mechanics tells you that a photon, a crystal, you, me, anything, has actually both characters, a wave and a particle character. Of course, for us, like I mentioned earlier with quantum tunneling, for instance, in the first lecture, we are too big, so we don't behave as a wave. We are a very bad wave. We don't necessarily have bad waves, but we are a bad wave. But light, or any particles, can behave both as particles and wave. And that is very important. And we don't have to be afraid of that, because it all makes perfect sense. Well, at least in a quantum mechanical way of dealing with that, it makes sense. So we see that next time how we can use that, and how we can use what we call the Young's experiment, or the so-called two-slit or multiple-slit experiment, to create qubits, but this time not, so with light again, not in a polarization state, or different state, or not in a polarization qubit, but has a spatial qubit. Remember I told you that we can have a photon basically here or not here at the same time. And that's what we're going to see next time. So, the photon as a qubit. So now, conclusion is what? The conclusion is, I take Maxwell's equation, I can show, this is what we call quantum optics realm, that Maxwell's equation can be quantified in a quantum mechanical way and provide the photon behavior of light, so the single particle behavior of light, not just the electromagnetic wave behavior of light, and that light is both a photon and a wave, and we just saw briefly today both of these aspects. But we also saw that photons, and in particular polarization state of photons, of light, can be manipulated in circuits like this. If I have a single photon and send it into some optical components, or like this one, which I'm going to demonstrate, we also saw that, so this could be a way of having our qubits going along, and as it goes along, so I can have different colors for different qubits, I can have different elements here and there, and those elements, as we saw, we just saw one as an example, can be these gates. So we have the Pauli gate, so the X gate, which is a NOT gate. We saw what it does is basically using one of those as a quantum gate. And we can manipulate these qubits as photons along the line with various gates applied to them. Okay? Like I said, there are other systems which behave the same way, which we're not going to necessarily talk about, like trapped ions, superconducting qubits, and so on. Another example we will give are electron spins, but you have to be aware that, of course, you know, when you start to go into physical systems, then you go into a different world. Because here, what I'm about to show you, what I've been showing you with light, you cannot apply the same things with electron spins, because it's not the same physical reality. A spin of an electron is not a photon of light. So you need different physics, different experiments, different measurements, different settings, and so on, and different problems. So how do we do that in a lab? Well, so here I have a way of mimicking a single photon. It's not a single photon, and I'll tell you why. But I've got here my source of photon. So I've got on one side here my source of photon. So here is what we call Alice, right? So this is the Alice side. So there is a laser and there is a polarization rotator, so I'll explain that after. And then on the other side, I've got Bob. Okay, I remember I told you that there's always Alice and Bob, one on one side for the source of qubits, and the other one for the measurement. And Bob has one of those polarizing beam splitters here. So one of those. And he's got two detectors. So those are the two detectors. And so what I'm going to show you here is how we can mimic a single photon qubit. I say mimic because, if you remember, I told you that harnessing single photon is actually a very difficult thing to do. So it doesn't work here on a simple bench like this. You need, you know, go into my lab and see what it looks like. It's a bit more complicated than this. So for this purpose, what I'm going to use is a laser. So this is a laser, which has a certain polarization of light, which is, I believe, vertical. And so if it's vertical, so that means light propagates this way. So I go from Alice to Bob, light propagates this way, and then arrive on this polarizing beam splitter. And if you remember what I told you, is a polarizing beam splitter is something that will select the polarization state. So in one polarization state, it will go through, and in the other one, so if it's like this, if it's horizontal, then it will be reflected. So when I'm about to press on this button, there will be a light pulse coming out, so not a single photon, but a light pulse. And I should see one of these two detectors going blue, detecting the light. Let's go for that. Now, if it works, of course. No, it doesn't work. Yes, I know why. So now I'm in the vertical state. So I'm in the vertical state here. So I've got the blue light always here. Why always here? Because, well, I'm in a defined polarization state, the zero state of the polarization, the zero state of the qubit. And here's a polarizing beam splitter that, by the look of it, lets the light going through when it's vertical. So always this one will click. See? I press again, I press again. Now, if I rotate, we said earlier that I can use elements like this. So it's the same one here. And I will rotate it, so this half-wave rate, that now I go from vertical to horizontal. So now this detector should click, not this one. Let's go. So if I do that, there we go. Now I was vertical, now I'm horizontal, and that's the blue light, this detector, which is the reflected part of the polarizing beam splitter, that goes blue. And now I can be in a superposition state where, so I rotate that, so now I'm in 45-degree angle. Okay? So 45-degree angle means that I have both, right? Vertical and horizontal polarization. This is what we had earlier on the board, on the blackboard. So if I go here, and if I am a single photon level, which I'm not here, but this is mimicking it, let's assume that every time I press that button, the light pulse here has only one photon, then that means that randomly, or half of the time, I should get an answer here, and then next time maybe here, and then next time here, and so on. So I should have an equal probability of having these detectors to click for one given photon impinging this polarizing beam splitter. So let's try. Of course, this one is not working properly. Let me see. This one clicks. This one clicks. This one clicks. This one again. It is random, so why not? This one, and so on and so forth. Okay. So now, this single photon at 45 degrees arrives on this beam splitter. This beam splitter separates both polarization, but there's only one photon. So the photon either goes this way, because it's been projected from the 45 to the horizontal, or it's been projected to the vertical, and then it clicks on this one. But it can only click once for a single photon. Again, this is mimicking, because actually this is a laser, so both of them should click at the same time. And I'll let you think about why that is. But for a single photon level, no problem. So this was plus 45, and I can do it for minus 45. And I should get the same thing. Minus is like this. So again, randomly, for each photon, I should get a click here or a click there. So let's try. So again here. Again here. Well, it's not so random, maybe. Well, okay, I guess this one should work. Well, maybe the alignment isn't so good. It's always the same one. So anyway, so this one was, oh no, okay, I see. That was my bad. So this should be, yeah, this is the 45, and this is the 0. Okay. All right. So with this simple demonstration, we see that how we can manipulate and how we can measure the state of the light, polarization state of the light, which in this case, a single photon level, will be our qubit. So this is what we use in the lab. So we use this type of equipment. So if you come to my lab, you will see exactly the same type of tools that we use. Next time, I will, on the physical part of the lecture, for the lecture 4, I will go back to the this spatial superposition of using slits and using path encoding, and I will show you how, nowadays companies, in fact, use this optical setup, but in a more integrated way. And so you don't need these bulky optics in order to manipulate these qubits. But this will be next time. I guess now we can stop here. So I thank you again for this, following this lecture. And next week, so same time, 10 a.m. or 10:10. We actually start at 10:10. There will be lecture number 4 on multi-qubits. And the notion, very important notion of entanglement. So thank you again.